Hey everyone, in this video I'm going to revisit some basic mathematical functions and operations. So to get started, in statistics and more generally in calculus, we often want to add a sequence of numbers that follow a certain pattern. And to the extent that the sequence follows a certain pattern, we often might want to express the sequence without necessarily writing down each individual component. So for example, suppose we wanted to express the sum or product of all numbers from 1 to 100 without necessarily writing down each individual number. And for tasks like this, what we do is we use the summation operator or the product operator, which is the capital sigma or capital pi that you see up there. So for summation, this usually looks like this. We have the sum operator right here with an index running from I to 100 of all elements xi, and this basically just stands for a sum with 100 elements of x1 plus x2 plus x3 all the way up to x100. And whenever we have a sequence like that, there are a couple of properties that we should keep in mind. The first one is, since this is a sum, whenever we multiply the sum or each element of the sum by a constant, in this case c, we can pull the c in front of the sum, right? So you can verify this by just plugging in c in front of each individual element here, and just like with basic algebra, you could put this c in front of that equation and multiply it in parentheses by the entire sum. Another property is that if we have a sum of two elements within this sum operator, so xi plus yi right here, then we can separate these two sums, basically rearrange them so that we have here the sum from I equals 1 to n of xi plus the sum from I equals 1 through n yi. Okay, so we can separate two sums in separate using separate sum operators. Lastly, if we have a sum of a sequence where we only where the only element is constant, so see the c doesn't have a specific index, then we can simply this is simply equivalent of adding c to itself n times, so we can of course then write this as n times c. Okay. So this is for the sum operator. We have similar rules for the product operator. The notation is similar. We have this capital pi from I equals 1 through 100 xi. So each element xi is multiplied in this sequence. So this is x1 times x2 times x3 all the way to x100. And there are similar properties, although we have to be a little bit careful since now constants are multiplied, they're not just added, right? So as soon as we have a constant times xi, in this case, we have to take care. We can't just pull out the c and pull it in front of the sum. We have to, since c is multiplied n times in this product, when we pull out the constant in front of the product sign, it has to be c to the power of n, of course, because c is multiplied by itself n times within this notation. More generally, if we have if this sum does not start with 1 but with I equals k through n, so it could technically start with a lower index number, of course, or with a higher index number rather, that is larger than 1. Of course, the power has to be adjusted. So depending on how many times we multiply c by itself, the exponent here changes, where now if we pull out the c, it is c to the power of n minus k plus 1. And then the remaining product. Um, the other thing to note is that as soon as we have a sum of two elements, xi plus yi, of course we cannot, since this is now a product of sums, we cannot simply separate them apart. So you have to be careful. This easy separation that we had with the sum doesn't work here. And lastly, if we have only a constant as an element of this sequence of this product of multiple elements, of course, then this is equivalent to multiplying this constant by itself n number of times. So this is c to the power of n. Okay. There are a couple of other useful functions that I'm just going to mention real quick. On the one hand, we have factorials, which we will need in the context of probability and combinatorics. Factorials, the notation for a factorial is this exclamation point, and this means if we take x factorial, that means that we take x times x minus 1 times x minus 2 and continuing this way until we reach 1. So 4 factorial would be 4 times 3 times 2 times 1. And we need this in combinatorics to count the number of combinations of certain sets. Another one that we see sometimes in programming is the modulo, which tells you the remainder when you divide the first number by the second. So for example, 17 modulo 3 is 2, right? Or 100, or an alternative notation is this percent. 100 modulo 30 is 10, right? So 100 divided by 30, the smallest, or the remainder, 3 times 30 is 90, so the remainder, and 4 times 30 is 120. Right, so this would be the remainder after division would be 10. In general, a lot of expressions, or in general, we will talk a lot about functions and expressions, and in general, a function is always defined as a mapping or transformation that ultimately relates members of one set of the domain to members of another set, which is usually called the range. And so in general, every function, every mathematical function that we're talking about is ultimately describes such a setting. And I'm going to show 2 examples in a second. The important thing to remember is that it is a unique mapping from the domain to the range. So in this, well, it's only unique in one direction in the sense that each element of the domain is uniquely mapped to one element of the range in the range, but of course 2 elements in the domain can be mapped to the same element of the function. Okay. So what does this look like in terms of explicit example? So for example, we have a basic function here of one variable that is a mapping from R1, so the set of real numbers, to R1, again, the set of real numbers. And one example for this would be f of x is equal to x plus 1. So this is now a mapping where from the set of real numbers x, for x, we basically map each number to x plus 1, right? So 1 is mapped to 2, 2 is mapped to 3, and so on. So in other words, for each x in R1, f of x assigns the number x plus 1, okay? And you can see, of course, every x, or every x in R1 has a unique mapping, therefore. Let me just zoom it. I'll go up here. Another option is, or In general, this mapping doesn't always have to be from a unidimensional space like R1 to another unidimensional space. It could also be from R2 to R1. So in this case, we have a function f of xy. So it's a function of two inputs, x and y, and that is defined as x squared plus y squared, right? And so in this function, we're mapping each ordered pair x and y, which is in R squared, so kind of in a two-dimensional domain, to a single number in R1, which is x squared plus y squared, right? So for example, the point 1, 1, x equals 1, y equals 1, would be 1 squared plus 1 squared, so that would be equals to 2, okay? All right. Oh, okay, sorry. There are a couple of general types of functions that we kind of should be aware of, and that you've probably also seen in either in undergrad math or in high school math classes. In general, the kind of one of the simplest types of functions are called monomials. So these are of the form f of x is equal to a is a constant, x to the power of k. So examples would be, for example, y or f of x is equal to x squared, or y is equal to minus 1/2 x to the power of 3. So those are basic monomial functions. More common or more frequent in terms of what you'll see is polynomials, and in general polynomials can be described as sums of monomials. So they're basically let's see. Oops. Oh no. Okay, sorry for the quick mix-up. So, polynomials are sums of monomials. For example, f of x is minus 1/2 x to the power of 3, right here, plus x squared, or 3x plus 5. So 3x plus 5 is also considered a polynomial, because you could think of the 5 as 5x to the power of 0. So essentially it contains still two monomials, okay? Sometimes we talk about the degree of a polynomial, and that is the highest degree of its monomial term. So the degree, or the degree of the monomial is k up here. A is the coefficient, and so this first example would be a polynomial of degree 3, okay? Okay. Then we have exponential functions, and for exponential functions, they're of the form f of x equals a to the power of x. So, for example, 2 to the power of x. Yeah. And as soon as we talk about exponential functions, one thing that we often see or that we move to is logarithms and exponents, or natural exponents. So in general, the relationship of the logarithm and exponential functions is, you can think of the logarithm function as the inverse of an exponential function. So if we have y equals the logarithm to the base a of x, that is equivalent of, or that implies that a to the power of y is equal to x, right? So in that sense, we can think of the exponent a to the power of y as the kind of inverse of the logarithm of x with base a, okay? In general, when we work with logarithms, the most or the two most common logarithms are of base 10 and base e, where e is Euler's number. So for base 10, what we often see, that means basically that the base is 10, so 10 to the power of y is equal to x. And the base 10 logarithm is often simply written as log x, so log x, without with omitting the base. More common in the applications that we will talk about throughout the semester are the natural logarithm with base e. So e is here the, as I said, Euler's number, and it is often written as ln x, but depending on the book and depending on what kind of notation is used, what we often see is that log, so log x, is also denoted the natural logarithm, especially in some statistics books. There are a couple of important properties of exponential functions to keep in mind. I'll just go through them real quick. So if we have two exponents with the same base, a to the power of x times a to the power of y, then we can summarize these by adding the two exponents. So this is equal to a to the power of x plus y. As soon as we have a to the power of minus x, that is equivalent of saying of 1 divided by a to the power of x. And by extension, if we have a to the power of x divided by a to the power of y, we can subtract both exponents and write this as a to the power of x minus y. If we take the exponent of an exponent, so a to the power of x to the power of y, then we multiply both exponents. So that is equal to a to the power of x times y. And as I mentioned earlier before, when we talked about polynomials and monomials, a to the power of 0 is equal to 1. Then second, properties of logarithmic functions, and these hold for any base, and as I said, in most cases we'll work with a natural logarithm. In general, the logarithm of a, or base a of a to the power of x is equal to x, so the logarithm and taking a to the power of x cancels each other out, just like a to the power of log a of x cancels out, and we're left with x. Okay, and this is just a consequence of the logarithm and the exponent being basically the inverse of each other. A couple of additional properties. Log xy is equal to log x plus log y. So if we have a product of two terms, we can separate the log, and or the log of a product is equal to the sum of the logs. And this is actually an important rule that we'll come back to. Log of x to the power of y, whenever we have an exponent, we can pull out the exponent in front of the log, so that's y times log of x. And equivalently, if we have log of 1 divided by x, since this is equal to log of x to the power of minus 1, we can pull out the minus 1, and that's equal to minus log of x. Then we have log x divided by y, which is similarly, we can kind of combine those rules and write this as the log x minus log y. And then the log of 1, in this case, with a natural logarithm, we could write as log of e to the power of 0, since e to the power of 0 is 1, and then pull out the 0 in front, and then we're left with 0. So one thing, as we move through this semester and going into the next semester, one thing that is important to keep in mind is that we can use logs to go between sum and product notation. And this will be particularly important when we're learning maximum likelihood estimation. Because ultimately we will have, we will have sequences that look somewhat like this. We have a log of a product over a lot of elements, and this is this log of this product can be expressed as the sum of the logs, which again, this is a property or a result that we will use in maximum likelihood estimation to simplify some equations. So we can again express a large product or the log of a large product as the sum of each individual logs. And this also more generally holds when we have some constant c in there. Again, since this is a product, if we want to pull this out, we would be left with c to the power of n times x1 through xn. And so then if we basically divide this into separate, or divide this into a sum of logs, then log c to the power of n turns into n times log c. Okay. So in general, sometimes when we're having a function, we might want to find how x varies as a function of y, and in these cases we might want to kind of use algebra to move x to the left-hand side of the equation and make sure that the right-hand side is only a function of y. Specifically, what we want to do is, if we want to solve for a specific variable, in order to find the roots of an equation. So the roots of an equation are those values of variables that cause an equation to be equal to 0. And we'll see in some of the later videos why that is ultimately important. Some examples, some examples kind of in political science, if you're doing game theory, in order to find equilibria, we need to find roots of functions, and also to do maximum likelihood estimation. Ultimately, what we're doing is we're finding roots of derivatives in order to find the maximum likelihood estimates. So it's possible that there are multiple roots, that there are multiple points of x where f of x is equal to 0. So here's just one example. F of x is equal to x squared minus 9. If we want to find the roots of that function, we have to set this function equal to 0. So 0 is equal to x squared minus 9, and then we want to solve for x. So ultimately, we start with this equation, we set this equal to 0, and then we add 9 on both sides, for example. Then we have 9 is equal to x squared, and then we take the square root, and so we know that x is 3, or plus minus 3. So there's a root, x squared minus 9 has a root at plus 3, and x equals minus 3. Okay. In more complex scenarios where we don't have just one x squared, but we have a quadratic equation of the form ax squared plus bx plus c is equal to 0, we can use the quadratic formula to find these roots. The quadratic formula for quadratic equations of this form is minus b plus minus square root of b squared minus 4ac divided by 2a. All right, that's it for basic functions. In the next video, I'm going to talk about limits.